When you're working with type classes in Haskell, then there are often situations in which you know that if you have instances for some classes, that there are specific rules how those instances allow you to define the instance of another class. And today we're going to look at deriving-via, which is a language extension that allows you to capture such rules, such relationships between type classes, and then have them available for you to invoke when you want them and to work with. And as to the specific example we're going to look at, I've been inspired by browsing the internet, and last weekend I found a post on Mastodon about the changes that were made to the monad type class in Haskell back in 2015 as a consequence of the Applicative Monad Proposal. So we're going to revisit the changes that this proposal introduced in this episode, and we will see how we can apply deriving-via to this particular situation.
Yeah, so welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, the show is live streamed, so we invite you to submit questions or comments in the chat, and we will try to show them on screen and discuss them.
Yes, okay. So let's start with a little bit of history. So here, side by side, we see two versions of GHC. On the left, we have GHC 7.8.4, which is quite old by now. And this, as far as I know, the last version of GHC that did not yet implement the changes of the Applicative Monad Proposal.
And, the good old days.
Yeah, and on the right, we see GHC 9.8.1, which I think is the current or the latest release of GHC. And actually, if we quickly look, the next release after 7.8.4 was 7.10.1, and in the release notes for 7.10.1 we have GHC has implemented the Applicative Monad Proposal. So that was sort of the big news then. So let's see what that means in practice. If we just ask in GHCI for the definition of monad here, we get this. And if we ask for the definition of monad here, we get this. So you see that, okay, so there are minor differences in the way GHCI introduces itself. There is this minimal pragma, which is not on the left. There are more instances being listed here. But the two main changes that you can see is that here we have a fail method that is gone. That is not actually the Applicative Monad Proposal. That was done later as part of the monad fail proposal, or I don't exactly know what that was called. And I think it was sort of less controversial. The Applicative Monad Proposal was slightly more controversial. And this is basically this innocent-looking extra superclass here, that this is what it is all about, right? Here, class monad has no superclasses, and here the monad class has the applicative superclass. And yeah, to start with, let's actually look at what is sort of the practical implication of this. I mean, so there are multiple practical implications and different ones, but one situation is that if you have a new data type, right, such as this arrow type here, which is like pretty much like maybe, and maybe is a very simple instance of the monad class, so that's why I chose this. Error is almost like maybe, only that it has a string, extra string argument in sort of the empty case or the failure case. If we want to make this an instance of a monad here in the old days, we would write instance monad error, where, and then we would write return equals OK. And then we would have to define bind, and bind we can define by pattern matching. So if the first argument is an OK, and then we have a function, then we apply the function to the value of type A within the OK. And if we have a fail with some message, and we have a function, then we actually don't need the function, then we just fail, right? That's the whole point of this kind of monad, that if we have any kind of failure, then we abort. And now I don't have Haskell language server for a JRC version that old, but if I actually explicitly load this, we should be able to see that this in principle works. Even this version of JRC is already warning, because it's sort of the last version of JRC before implementing this proposal, and it was already decided at the point. So even here we are getting this warning that error is an instance of the monad class, but not of the applicative class, and that this will become problematic. But in this version, we can do it, right? I mean, it's accepted like this. But if we try to do the same here, right? If we actually, I think I have prepared this. So if we try to do the same here, I do actually have Haskell language server active, and we can already see that GHC is complaining. So there are actually two different complaints, but the one that we're kind of expecting is that we get an error that there is no instance for applicative, because applicative is a superclass. And we also get some interesting warning about a non-canonical return definition, to which I'll come back later. Right, and this is, I mean, this is not a surprise in the sense that, like, even if you look at these release notes that I've already briefly shown, if you go further, it says, this is a breaking change and your programs will need to be updated. Please see the GHC 710 migration guide on the GHC wiki. And the GHC 710 migration guide is then giving instructions for what to do. But rather than reading these instructions now, we're just going to try this ourselves and replay essentially what these instructions are saying. So if we zoom in on this now, right, and try to fix it, so then we have to give a definition of, or an instance definition of, applicative for error as well. And applicative is a class that has two methods, or two prominent methods at least. I mean, two that you have to define. One is called pure, and the other is this star operator, right? And the type of pure, let's write that out, is for all A. In this case, we have to give something that goes from A to error A. And in the case of star, we have to do something that goes from error function of A to B to error A to error B. Now, the type of pure is more or less the same as the type of return. And in fact, I mean, in principle, we could get the idea that we can just set pure to return. And that is accepted. It again produces a warning that I'll get back to later. In the case of star, we could start thinking about the constructors of our error type, but actually there is a way to say that if we have a monad instance, and we do for error, then there is a sort of canonical way of defining star, and I'll call that function app for reasons that will become clear, and try to define it once and for all. Right. And here we are getting in like M of A arrow B, which I'm going to call MF, and we're getting an MA, which is this argument here. And then we can use do notation because we are in a monad, and then we can extract the F, the function, from MF, and we can extract the suitable argument from MA, and then we can simply return F applied to A. And that's kind of the behavior for app that you would work, and there is nothing particularly spectacular about it, and then we can define this here. But now, like, even disregarding the warnings, GHC is still not happy, because applicative also has a superclass, namely functor. And we have to define that one as well. So we have to go and define instance functor error. And for functor, we have to define one method, which is called fmat, which in this case is for all A, B, A to B to error A to error B. Right. And again, we can define this directly on the constructors of error, but also, again, there actually is sort of a canonical way of defining fmap if we have return and bind, namely, and in this case, I will call this lift m for reasons that will also become clear. Namely, what do? We're getting a function, and we're getting this MA, and again, we can use do notation, and we can run the MA and extract the A, and then we can simply apply after that the function f to it, and then we can set fmap to lift m, and then this is fine. Now, the only thing, at this point, it actually works, right? At this, like, I mean, these warnings, there are warnings, and if we were to try to use our instance now, if we were to call a function such as, say, join, which takes like an error of something and collapses it down. So if we like do something like join of OK of 5 and try to evaluate that. For that, I actually have to import control monad join, because join is, of course, not in the prelude. Then I have to define a show. That's all valid, a show instance for error. But yeah, then it actually works, right? So this definition is okay. So let's try to reflect on this a little bit, because I mean, at the moment, so there is still this non-canonical warning left. So what's that about? Well, actually, there is sort of another proposal, which I think was mentioned on the channel even before the episode started, the monad of no return proposal, which is aiming at removing the return method from the monad class, because like now applicative is a superclass and pure is already defined there, so return is kind of redundant. And as kind of a preparation for this, GHC is trying to enforce that you're actually defining not return, but pure to be the meaningful function, so that you're putting OK here, and that you're then using return equals pure, which actually is the default definition these days, so you don't have to write it at all. And then this warning disappears, right? And so I'm not sure whether there actually is a decision to remove return at a particular point. I haven't like looking up at the current status there, but these warnings are basically given as a preparation for when that might happen, right? And then the other thing, to be fair, is that lift m and app, you don't have to define yourself. They're already in control.monad. So if I simply import all of that module, I can actually remove lift m and app from here, and then I'm ending up with this. But this remains, right? And if you contrast the two versions, if we go back to this view, if you contrast the two versions, then there's quite a bit of additional boilerplate in this new world than in the old one, right? And that's kind of the origin of sort of my inspiration that I mentioned in the introduction, because when I was looking at Mastodon during the weekend, I found a post by Martin Escardo. Let me bring that up briefly, where he's like teaching a Haskell course apparently at the moment to his students, and he is kind of complaining about the new definition. So he's writing the old definition here, class calling it monad prime, and then he's like giving the sort of in comments the set of new classes and how they are defined, and then he is presenting an interesting observation, namely that you can translate from the old definition to the new definition by essentially doing what we just did, right? By writing the system of instances for monad, functor, and applicative, where you're defining fmap to be like, he's written out this in explicit do notation, but essentially as like we did with like as to be lift m, and implementing the star operator. Again, this is done explicitly here, but essentially as we did with app, and then setting pure to the old return, and bind to the old bind, right? And that is essentially the same thing that we did, only that he is doing this by defining general instances that say, like, if we have sort of an old monad M, then we can define a new monad M. And if we have an old monad M, then we can define a functor M. And if we have an old monad M, then we can define an applicative M. So let's actually look at this. Right, so this is first of all, it's an interesting observation, and it seems like it could be a solution to mitigate between sort of the two worldviews. So I'm trying to the full screen here, and I've been preparing this here as well. So I've ever so slightly renamed this from monad prime to be better able to distinguish this to classic monad, but I've called the methods return prime and bind prime as well. And then I've defined this system of general instances where I'm doing I'm going from classic monad to all these three classes. And so the first thing that you observe is that JC is complaining about these kind of instance definitions and is requiring us to actually enable a language extension that is called undecidable instances. Now, this undecidable instances makes some people feel uncomfortable, but not me.
I'm fine with it too.
I'm perfectly happy to enable that if it helps me. The only thing it tells me that is sometimes the type checker may bail out because it can't solve something. But the good thing is always, right, if the type checker checks your program, right, then you're still good, right? So that's why undecidable instances are not really problematic, right? It only says something about sort of certain programs you might write might lead to the fact that the type checker cannot actually solve the problem anymore, and it doesn't actually loop it, that it has some kind of threshold. And now the next thing you observe is that GHC starts complaining about the error instances that we've given, but of course we don't need those anymore, right? Because we have now given general instances. So these are in principle no longer needed. And at this point, we can try to verify that join OK05 hopefully still works, right?
So because we have a classic monad instance for error, right? I mean,
because I've also given a classic monad instance of error. Yeah, that's a good point. Thank you, Etzko. That is defined exactly in the same way, right, as we defined our monad instance for error here, right? I mean, but that one is still a necessary ingredient. Yeah. Now, perhaps I should also briefly mention that sort of even independent of the other stuff, for both the solutions that we had, it is actually rather remarkable that it works, right? It's not just the boilerplate, but it is also sort of the way that the recursion or the dependencies are going that is actually, not completely trivial, right? Because, the monad class depends on the applicative class, and the applicative class depends on the functor class, but then methods in the functor class, namely fmap and star, are defined as functions where we rely on the fact that the implementation, not just the type, but the implementation is given just in terms of return and bind, right? So that this doesn't loop depends on the fact that nobody comes and says, oh, the app method in control.monad could actually be generalized to work on any applicative if we just set it to be app, because then we would have a real cycle, right? And a non-productive loop. It really depends on the fact that app is actually defined as we had before. And in that sense, perhaps even Martin's version, where he is explicitly spelling these out, right, is safer, right? But ours still works. Right?
No, to be fair, this is a common pattern, right? If nobody is going to change this definition of app to be applicative only because every code in the world will break. But But it is subtle.
Yeah. Now there is something to be said about this. Like, I mean, you could think that we are done now, right? But I would actually argue that defining instances like this has significant drawbacks. And the reason for that is that, like, colloquially, we are typically saying, like, if we see an instance like this, then what this instance says, we often read it like, if there is an instance for a classic monad of M, then we can produce an instance of monad M such that, right? But that is not really how GRC looks at it. GRC looks at these instances by disregarding the context and is looking at them, oh, here is an instance that, like, I can use always, like, to make anything a monad, right? And, oh, by the way, afterwards, I should require that there is a classic monad of M instance. But this is really more reflecting the approach that GRC takes. When GRC searches for instances, it completely disregards what's on the left of the double arrow. It only looks at the right, and it finds sort of the best matching instance by just looking at the right-hand part. And then it commits to that instance without any potential for backtracking and simply tries to solve the preconditions.
Yeah,
and that means that,
since this is a variable here, monad M, for just any M, this is by definition the most general instance you could possibly have.
Yes. If you have something which is completely unconstrained, it always matches, and you're basically saying, this is the one and only instance I'm ever going to give. Now, you can still, like, weaken that a bit by, like, resorting to overlapping instances. So we could make, like, our original instances that, like, we got complaints about now, we could kind of make them work, I think, by adding overlapping pragmas here. Actually try that. Perhaps not even that works. I haven't actually tried it. So this is always a good idea to try this the first time. But I think if we add all three, then in this particular case,
I guess we didn't try this ahead of time because neither of us is actually particularly fond of overlapping instances.
Yeah,
like
but I mean,
unlike the citable instances, this is a pragma.
Yeah, overlapping instances are kind of difficult because the point is instance scoping is weird, right? Instances don't really have a scope. They scope over everything, but nevertheless, not every instance is actually known to GRC at every point in the program. And that means if you have overlapping instances, you have to delay instance resolution, because if you resolve an instance by using a general instance, but a more specific one becomes available later, then you regret this, right? So, like, overlapping instances lead to their own problems. But even if you accept that, right, if you're saying whenever we have rules such as this, like if we have a classic monad, we can form a monad and an applicative and a functor out of it, that's just one of many possible rules, right? We all know that there are applicative instances that are not an instance of monad, and there may be other rules that can be used to form an applicative instance if you have a bunch of other type class instances available. And certainly the moment you write another instance of the form instance some other classes, right, applicative M, where ... anywhere in your code, right, you have a real conflict that can never be resolved, and there is also no real way out of that anymore, right? So that's why, like, I think, like, wanting to write these rules is perfectly understandable, but it is not practical, right? So this is where deriving-via comes into play and gives us what I think to be a better solution. And what's the idea of deriving-via? Well, I mean, I already said conceptually in the introduction, the goal is indeed to just, like, take such instance forming rules and make them controllable, like to give them a name so that we can invoke them when we want to use them. But the vehicle to give them a name is new types. And so I'll show you how that works. So we start by defining a new type which I'm going to call from classic monad, which has two arguments, m and a, and a constructor. And it contains just an m of a. So that means that if I have from classic monad ma, it is guaranteed, that's the property of new types, to be representationally equal to an m of a, right? And have the same runtime representation. But as far as the type system is concerned in Haskell, it's different. And that means we can give instances for from classic monad m that are different from the instances for m. And we can kind of fix the universality of these rules by defining these instances for from classic monad m now. Of course, that also means they're no longer automatically applicable, but we'll see in a moment that this is actually exactly what we want. And of course, we get errors now. I'll get to that in a moment as well. All right, so if we do this, then return and bind are no longer entirely type correct, right? Because like, what do we need now here for pure? We need something that goes from A to from classic monad MA, but return prime is going from A to M of A, right? But M of A and from classic monad M of A have the same representation. And if things have the same representation, we can convert between them. We can either convert by applying the new type constructor, or we can convert by applying safe coercions, which we've already mentioned in some other episodes. So I'll do that again. I'll import data.coerce. And this is not unsafe coerce, right? This is like type-checked safe coerce that we're only coercing between things that actually have the same representation. And so I want to call coerce, but unfortunately I have to help the type checker here, because if I just write coerce return prime, this would be so nice if I could do that. I'm getting things where like GHC cannot infer that the type variables are actually the same. So I have to explicitly instantiate return prime to the type argument m and to the type argument a to make GHC happy. But then like this is actually fine. And I can do the same thing for bind for all a, b, ma, oh, actually not ma, but from classic monad ma, and then a to from classic monad mb to from classic monad. I'm already seeing that I have been shortcutting from classic.
I didn't even see it.
Monad mb, right? And then here I need to coerce again, and then I have to apply m, a, and b. And now it all goes through. But like, because it's coerce, we can see it's the same function. Coerce is a no-op at runtime, right? So we are really just using the same definition as before, but giving it a different type. And so the main achievement in a way so far already is that we no longer now have one of these universal instances that are problematic that match everywhere, but sort of the drawback, or at least the apparent drawback now, is that also we cannot use it anymore for our error type. Like, I mean, obviously we want to get rid of these original instances here again now, because we want to define our new ones. I cannot, like, I don't automatically have it available for my error type anymore. But this is now the beauty of deriving-via, is that I can choose to steal an instance from any type that has the same representation using a deriving clause. So what I can do here is I can add yet another language extension, deriving-via, and I can add another deriving clause. And here I can now say I want functor, applicative, and monad via, and here I have to give a type that has this instance that is representationally equal to error. But that is from classic monad error. Because from classic monad error is, by use of this new type, representationally equal to error, and has the instances that we want. So this is the extra thing we now have to write, but these rules we have to write only once, right? Unfortunately, they are not right now in a library, but we have to write them only once. And then for a new type, we can simply write this, right? We have to give the instance for classic monad, of course, like we have, but we have to only define return and bind, like in the old days. And then we can get, like for the new monad, for the new applicative, for the new functor, we can get this for free. And again, I should actually probably, I don't know, delete this and try to reevaluate and see that it still works. Yeah, but I mean, I have not made a mistake. And I think this is a good example because, I mean, deriving-via has many, many applications, right? I mean, there are many things that are representationally equal to each other, and you can lift class instances around in many ways. And JC had for a long time, it had generalized new type deriving, which basically says you can steal an instance from the wrapped type and make it available on the outer type, right? If you define a new type, you can like derive instances for this new type by taking instances, inheriting instances essentially from the type you're wrapping. But that's just a special case of deriving-via that is subsumed by deriving-via. You can like coerce instances between any two types that are representationally equal. That's a very powerful concept, and we've only shown a single example in this episode, right? But I think it's a nice example, and it also shows that you don't necessarily have to argue a lot about sort of what is the one blessed way of organizing your superclass hierarchy or of deriving one instance from another, because you can just give names to all the different ways and then say which one you want, right? By actually spelling it out. And that, like, being explicit is often better than being implicit. Okay, I've been talking a lot. Do we have any questions?
We do. It's a little bit of a slight tangent, but maybe it's nonetheless useful to discuss it slightly. It's in two parts. So the first is both are by Glyn. So if you have time, would you care to comment on the benefits of this proposal, which presumably outweigh the disadvantages? And he follows up by something that I think I don't know, for example, with a monad that is not applicative or a functor cause some semantics problems for users of monad.
Yeah, so that's a good point. I can say a little bit about that, although I'm not sure whether I'll cover all the nuances or corners of your question. But so, of course, there are advantages of the proposal as well. And one of the advantages is that often, of course, for a data type that is an instance of monad, such as error or maybe, right, you do want the applicative and the functor methods as well. Right? I mean, you do want to map over a maybe, or you do want to just write something like, I don't know, another example would be something like lift A2 of plus of just 3, just 5, and have that be just 8, right? These kinds of things. And so there is a rich interface of monadic operations, but many of them are actually already working for applicative, and you don't want to duplicate all the names. So in many cases, you do actually want to have all these methods available, and you actually would also like them to be compatible in some way, right? And you actually want to relate the classes to each other and say that you better have an applicative instance that is compatible with a monad instance. And so by tying these things up together, you make it easier to avoid unnecessary redundancy, and you also make it easier to specify the relationship between these classes and in which ways they should be compatible with each other. And another thing that I briefly wanted to mention is perhaps it's surprising from today's perspective why this change was suddenly made in 2015. Why was monad not always like a subclass of applicative? And the reason for that is yet more history, and that is like the monad class in Haskell is actually pretty old. It goes back to I think 1996, it was introduced in the Haskell standard 1.3 which was released in 1996. So that was before Haskell 98, which was sort of the first stable, and that introduced constructor classes, that is type classes that are parameterized over type constructors, such as functor or monad, like for the first time, and it introduced monadic I/O, and but it did not introduce applicative, and applicative as a class did not actually exist in Haskell until 10 years later in 2006, when in the GHC release 6.6, there was like a new module control applicative was introduced, right? So just for simple historical reasons, right? Applicative came much later, and yeah, at that time, I mean, it was already clear that it's between a functor and a monad, but at that time, monad still had no superclasses, and there was already this discussion about, oh yeah, but if we change it, then it's actually like a change that also causes breakage, and it took quite a bit of time still after this introduction of applicative to then like come to some kind of consensus. I think I've not like probably answered all aspects of the question, but hopefully said like a little bit that helps.
Yeah, it's a lot. I mean, one comment to make is that this cannot happen, right? You cannot have a type that is a monad but is not applicative, right? So that is not possible.
Now it is like, I mean, it's conceptually not really possible. It's conceptually not really possible, but now it's also in practice not possible, right? I mean, before you could have that, but yeah.
Okay.
Yeah. Okay. Then
shall we wrap it up there?
Yeah. If there are no more questions, then let's wrap it up.
All right. So thanks everyone for watching this episode of the Haskell Unfolder. If you enjoyed it, please like and subscribe. Feel free to leave any comments. We'll leave the chat open for a few more minutes. So if you want to ask any questions in the chat, feel free to do so, and we'll try and answer them. And otherwise, you can just leave them in the comments below, and we'll try to address them offline. We should see you, everybody, again in, I guess, 2 weeks, although that might be Christmas time. We haven't actually discussed that. We'll announce when the next episode will be.
We'll announce, yeah.
Yeah. All right. Thanks, everyone.